on what I just showed while I get my PowerPoint up and running. So you heard Penrose talk, and what Penrose was saying was that there are physical things, and then there are these other stuff like they're made of this, then they're made of that, and you keep going down and down, and it comes down to protons, electrons, neutrons, quarks, and stuff. And then at the end he says that the best description that you can give for what an electron is a mathematical description, that electron is something that obeys the Dirac equation. Does anyone see what's the problem with that? Yeah, we are not able to not just about visualizing anything, but electron is a physical thing. Remember that in our last lecture we talked about what is physics and what is a physical thing, and the way we define physics is it is the rigorous study of the physical world or physical things. And a physical thing is something now, and it can become something else later. A physical thing is characterized by its existence and the fact that it can change. And the primary property of any physical thing is to have extension. By extension, I mean, if I have this pen is extended. By that, I mean it has one part outside another. That's the basic definition of a physical thing, that it has one part outside another. That's not a mathematical equation. And when you're saying that electron is something that obeys the Dirac equation is not the first. It's not that light looks at Maxwell's equations and follows what they dictate. It is that light is primary, or electron is primary. Electron is what there is. And then from there, we are trying to derive something. It is not that the electron itself is something that follows a law that you made up. And we have to note the distinction here very clearly, because then if you don't note that things come from the physical reality, it just becomes mental gymnastics, right? Electron is not defined in terms of some mathematical law that is made up by the human mind. That's not the definition of an electron. An electron is what it is. It is a physical thing. And so it's not an equation. So if I say what is a tree, and let's say I make up an equation that a tree is something that obeys Podila equation, right? That doesn't define a tree. A tree is a tree, right? A tree cannot be defined by Podila equation, because Podila equation would be something that I would make up in my mind. And so that's the problem there. And in the first audio clip that I had shown you, that's from the BBC one, there at the end, the lady says that she doesn't know where math comes, she does not know where math comes from. And despite not knowing what mathematics is, people often make statements, grandiose statements like God is a mathematician, or they make statements like the universe is written in the language of mathematics. Like, for example, this is often attributed to Galileo, that the universe is written in the language of mathematics. So we're asking the question, is the universe written in the language of mathematics, or put it another way, is mathematics the language of the universe? So we need to understand where this math comes from. What is mathematics? So recall that when we looked at what is a physical thing, we saw that a physical thing is something that exists and something that can change. Right? And now we also talked about what is a substance and what is a property. So we saw that a substance is something that can exist by itself, whereas a property is something that exists as a part of the substance. For example, you could say that an apple would be something that is by itself, but color is something that only exists as a part of this thing, right? You cannot imagine color by itself. So that's what we mean by substance and property. So the first primary property for any physical thing, what is the primary property for any physical thing? Does anyone recall that from the previous lecture, or does anyone want to take a shot at what is the primary property of a physical thing? Yeah, I would like this to be more interactive, so that um, any lecture is made up of two parts, both students and the teacher, right? So if I'm just going to talk to the screen and you guys are not chipping in, then we cannot make much progress. So I would like you to chip in and sort of recall from the previous lecture how we define the base property of a physical thing. Sorry, anything that is okay. Anyone else? Someone else was this saying something, right? So so things exist and things change. That is right. But the primary property of a physical thing is having extension. That is, any physical object is extended. That is, any physical object has one part outside another. Take any physical object, even if it's an electron, it must have one part outside another. It is not parts like in the sense of a proton made up of quarks. Electron is the elementary particle, but it still has extension. It has some length, some width, some radius. It's not a point as in your abstract imagination where it has no length, width, or height. An electron is a real physical thing that has some radius, let's say around 10 to the power minus 16 or whatever centimeters, that in fact can also be seen experimentally. So it is a physical thing. The primary property is extension, and by extension we mean having one part outside another. So you have multiple parts in a physical thing, and this is often referred to also as quantity. So quantity is having one part outside another. That is the primary property of any physical thing. You cannot think of a physical thing that does not have extension. If it does not have extension, it is not a physical thing. Any physical thing must have one part next to another. Those parts may be small, those parts may be really little, but it must have some extension, some size. Without some size, some extension, you cannot have the physical thing. And I don't like to use the word dimension for it, because dimension is a word that you use equivocally for different things like 2D, 3D, that comes from a coordinate system. But coordinate system is secondary. A coordinate system is not the primary thing. That's the kind of thinking that I want you to come out of, that there is whatever physical reality that there is. A coordinate system is you are making up the coordinate system to try to capture some parts of this physical reality. So those dimensions are something else. But here, more proper way of putting the primary property of physical thing is that it has quantity or extension or having one part outside another. So this means you can look at this in two ways. Having one part outside another or having size is, it gives you directly the idea of number. That is, a thing may have a number of parts. For example, if I take an apple, I can cut it into 100 pieces, right? That 100 is a number. And at the same time, because these parts are next to each other, all these parts share a boundary. These are not disjoint parts. For example, if you look at a computer or a phone and you say this is a thing, or you look at a human being and say this is one person, then that person's fingers are not different from that person's body. They are part of him, right? And so you can define a shape, a boundary for this person, that this person looks like this, that this person has this kind of a shape, or this object has this kind of a shape. So even shape comes out of the primary property of physical things. So studying this primary property of physical things is mathematics. So we abstract out other properties. For example, when I say I'm looking at orange, I'm abstracting out the color orange, I'm abstracting out it being a fruit, I'm abstracting out its mass, I'm abstracting out all these qualities, meaning I'm turning them off and only taking its shape, and I'm saying this orange is of spherical shape. So I'm able to abstract just the shape of the object by turning off, by mentally turning off other properties of that object. That is, an orange has several different properties. An orange has mass, an orange is at a certain temperature, an orange has other properties, but I'm turning off all those properties and I can just abstract out just the shape of the orange and say that is a sphere. Right? So these two would be the primary ways, number and shape would be the primary ways in which we study the primary physical property of physical things. And the study of number is arithmetic, whereas the study of shape is geometry. And we can build a bridge between these two by using analysis. That is, I can use algebra to combine geometry with arithmetic. That is, for example, if I draw this is a line. There is no equation in this line. It's just a line. But I could also write this as y is equal to ax plus b. This y is equal to ax b, it's an equation. There is no line in it. And in the line, which is a geometric feature there is no equation in it. What I am doing by bridging this gap of analysis is that I'm saying this line corresponds to this equation and this equation corresponds to the line. So you cannot define a line in terms of y is equal to ax plus b. A line is not what obeys y is equal to ax plus b. A line is a line. It is a set of points. And then if you choose a particular coordinate system that you make up in your mind and give some symbols, some meaning, like y is the vertical axis, x is the horizontal axis, a and b, a is the slope and b is the intercept. If you give these things in your mind and write this equation y is equal to ax plus b, then that's what is you're using to as a correspondence, as an analogy to sort of indicate the line as a symbol. But a line is not defined by that equation. A line is a line. A physical thing is a physical thing. A physical thing is not defined by an equation. I hope I'm making sense. Are there any questions in how a mathematical equation cannot define a physical thing? It is the other way around. It is from the physical thing, that is, we see physical things, so we see the primary property of a physical thing, that is quantity, and from quantity we abstract number, and then we abstract shape. So we get arithmetic and geometry, and we build a bridge through analysis. So mathematics comes from the primary property of physical things of having extension. That is where mathematics is. So mathematics, properly defined, is the study of quantity. Here by quantity we don't mean just number. We mean by quantity we mean extension. So it includes number, arithmetic, it includes shape, that is geometry, and the analysis that combines, like y is equal to ax plus b corresponding to a line is an analytical way of showing something geometric. Any questions about that? Yes, we are going to come to that. Whether we can use mathematical to describe. We cannot use mathematics to define clearly, because mathematics itself comes from physical thing. And what do we mean actually by a description? What are we describing? We have to be aware of that. So to look at that, let's first, um, take a little bit of detour and look at geometry, right? So often you hear from people about Euclid's elements, and that as the starting point of geometry. This is a very big misconception, because there is a much older Indian text called Shulba Sutras, which means measuring by the rope, literally principles to measure by the rope, and this went on to show that how to actually find a square root of a number purely from geometry, right? You know how to find a square root of a number probably using a calculator or some other algebraic method, but how do you find square root using just purely geometry, right? So what Shulba Sutra says is, if you take a square of unit side, that is, you take a square with one unit as the side, then it says the diagonal, whatever is the diagonal, you take this diagonal and you make another square of it, right? So you take, let me draw the diagonal in a different color so that it makes more sense. So you take this diagonal, you draw the diagonal, and you measure a row that is as long as the diagonal, and then you make another square with the diagonal, right? Then basically it says the area of this, area of the red square, and this area of the square made by the diagonal, area of the purple square, are related, and the relation is the area of the purple square is twice the area of the red square. And you can see that easily now using algebra, like this is 1 and that is 1, so this is square root of 2, right? So if I make a rectangle, a square with side of square root 2, then its area will be 2, square root 2 times square root 2. So area of the purple square made with the diagonal here would have twice as much area as the red square. And so that's how, it's a nice way of calculating square root 2, and in fact it shows a geometric way in a very, very clear demonstration to show that square root 2 is in fact irrational. Think about how you can show square root 2 as an irrational number using algebra. Algebra, if you use algebra, it takes 3 steps, but the Shulba Sutras, they're just beautiful, that now it says that you have this square that is made by square root 2, right? Now you try to construct this by tearing up different squares, different numbers. Can you construct this by tearing up different squares? So it actually sort of goes into kind of a calculus. I don't want to go into the detail. All that I wanted to mention is, initially we started out with geometry, whether it is Shulba Sutras or whether it is Euclid's element. Whatever it is, we started out with geometry and number, because number and geometry are directly apparent to us from the nature of physical things. Algebra is not natural. Algebra is that you have to think about some symbols to sort of identify these geometric concepts. And that started, in the modern sense, that started with Descartes. What did Descartes do? Descartes took a point and gave it a pair of numbers. So Descartes constructed what we now call a Cartesian coordinate system, that instead of calling this a point, now you can label this as x and this as y. So I can give each point, I can call this point as 1, 0, and this as 2, 0, so on and so forth, and this as 0, 1, and this as 0, 2, so on and so forth, right? So Descartes actually did this, and from here is how we are able to now say, I have a line, and this line is completely geometric. There is nothing equational about it. This line is what exists, right? And by giving each point in space, by defining a coordinate system and giving each point in space a pair of numbers. Here we are using x and y as general symbols, as a stand-in for certain numbers. So x could be any number, y could be any number. Once you plug in those numbers, you would get a specific point. but you are able to express the important point, the most profound point is you are able to express all the points in a 2D plane as xy, or I can express any point in the universe with xyz. Xyz denotes any point in the universe. I just have to plug in a coordinate system and pick 3 numbers to go there, right? So that's very profound, because now instead of drawing shapes or instead of counting numbers, you have just come up with symbols as substitute, and now you can just manipulate these symbols, right? And this makes life so much more easier. Now, the main modern scientific method that Newton had come up with, that in terms of calculus, is using this idea of describing something geometric, the physical shape. Shape is physical. Shape exists in a physical thing, right? So you see line because you see physical things that have different sides. You see a tree or you see a stick, and then you can abstract a line from that physical property of a physical thing, right? So these geometric shapes exist in physical things, in physical reality, and lines or other shapes are things that you are abstracting. You look at the moon and you abstract a circular shape, right? Because we have the ability to turn off other properties, that is, moon is white, or moon is not here, or things like that, and just take just the shape out. Now, instead of just looking at the shape as a circle, now I can say, x squared plus y squared is equal to r squared. This is a very beautiful way of correspondence, because x squared plus y squared is equal to r squared describes any circle, in the sense that, when you think about a circle, you are not thinking about a particular circle. Even, let's say, somebody who is not educated in mathematics, and you ask them, do you understand circle? And they will understand circle even if they haven't had any formal education, because they have the physical experience of looking at circular things and they have abstracted it out. And when they think about circle, they're not thinking about a particular circle. They're not thinking about a red circle or a white circle or a yellow circle or a circle with certain texture or a circle of 2 centimeters radius or 10 centimeters radius. They're thinking about a circle in general. And this x squared plus y squared is equal to r squared is not describing a particular circle, it is describing any circle, right? So because we can reflect, the human intellect looks at the physical world from the point of view of particulars. That is, our senses can only react to particular things. That is, my hands can only react to the coldness of a particular object. That is, if I am in contact with a given cold glass of water, then only my skin can actually feel that coldness, and that's how I get, the feeling of coldness. But even if I am not in touch with any cold object, I still understand coldness in general. So when I think about coldness, I don't have to think about that particular glass, that specific glass that I touched. I understand coldness in general. I understand coldness as snow in Himalayas, or I understand coldness as ice, or I understand coldness as something else. I understand this concept of coldness in general. So our human intellect is about abstracting from our sense knowledge, which is very particular. We get our sense knowledge by looking at particular things, particular physical things. We are abstracting general ideas. So we are always going from particulars, that is our senses, to generals. And this is the general way in which we understand. So in fact, the way science is described in Sanskrit is Vaisheshika. This is Kannada's Vaisheshika. Vaisheshika means Vishesha, which is particulars. Particulars of an object. You see a particular object, you see an apple, and then from that you abstract that color, that a physical thing like an apple can have the property of color, and you understand color in general as a property of a physical thing. So whatever you understand as general is Samanya. Samanya is not normal, Samanya is what is general. So you understand the general principle. So in Sanskrit, science is Samanya Shastra, meaning something where you understand the general principles. So to understand the general principles, and in order to convey these general principles, you need a system that can reflect these generalities. That is, for example, when I say circle, I have looked at several particular circular objects in my life. I looked at idli, I looked at orange, I looked at moon, I looked at so many other things in my life that look circular. But I abstracted the notion of a circle intellectually, even if I don't know the mathematical definition. I understand this idea of circle intellectually as a general idea, So next time I see a circular object, I can identify that it is a circle because I understand what is circle in general. I don't understand a specific circle that is 2 centimeters radius or 4 centimeters radius. I understand all circles of any color, any texture, any radius. I understand all circles all at once, simultaneously, with the idea of circle. That is the general understanding. I hope you are able to follow me. And so our science is about abstracting these general principles from particulars. So we need a way to reflect these generalities. And when you look at this algebraic equation like x square plus y square is equal to r square, it is somehow capturing this generality. It is somehow capturing this generality of physical things. That is, x square plus y square is equal to r square describes any circle in 2 dimensions, right? So we are able to reflect that generality in this thing because this equation ultimately is also abstracted from physical things. And that's why mathematics works so well, because mathematics is corresponding to reality that comes from physical things. The origin of mathematics is in physical things. I hope I made sense with particulars and generals. Any questions here? Okay, so am I making sense, or are you following me, or am I being please let me know, so because the next following steps that I would like to do depend upon this concept. Okay, so now we have looked at this particulars and generals. So now let's look at how we are going to use mathematics to actually describe physical reality, right? That's the question Denny also asked. So now look at, let's say you have a ball, right? And you can drop this ball. And at any given time, you can look at where this ball is and note how far it has moved. So as you are dropping the ball, you can basically say, okay, it reaches this point. When after 1 second it reaches here. After 2 seconds it reaches here. So you can see that and look at that and then plot a graph. That is, I can say 2 axes. One I am going to call, let's just call it x for now, and this I'm going to call it y. And then I see that the motion would be a parabola, right? Why it is a parabola, we'll come to that. But here we are dropping the object and we're looking at where it is at different points and then just noting that out on a plot. Now I say that this is a parabola and there is no motion in this parabola. This parabola is a parabola forever. There is no potency in this parabola. And there is no parabola in the motion of this ball. This ball is just falling down. There is no parabola in it. It is something that I am abstracting from there and plotting it as a shape. What do I mean by there is no parabola in this ball's motion? What is motion? Motion is change of place, right? Going from one place to another place is motion. But then what is change? Change is actualization of potential. What do we mean by that? That when I start this, when I'm holding the ball here, the ball is here. That is its act, meaning the ball is actually here. The ball is only potentially here, right? The ball has not yet gone there. The ball is right now here, so that is where it is actually, that is its act. It can potentially go to this place here. And then when I let it go, the ball actually moves here. The ball in reality moves from where it is to this place, and after it has moved, then the ball is here. Now it is here. So what was potentially possible has now become actuality. That is, to begin with, the actuality was that ball was here and potentiality was ball was there. But when it moved, that potentiality of the ball being there became the actuality. So the process of potentiality becoming the act is what we call as change. Actuality is the existence, and when change happens, its potential is actualized. That is, the ball could be possibly be there, and so it has potency to be there, but when it moved, that potency has become actuality. Now the ball is there. So that is what that change is. But if you look at this parabola, there is no such potency there. That is, this is actually what already happened, that the ball started from here, it went there, 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 it went here. So all these times are sort of all at the same time. In the sense, you have already actualized it, you have already seen it. So there is no more potency in this graph. This graph, if I draw this parabola, this is going to just look like a parabola forever. It is never going to change. It is just a graph. It will never change. This parabola is a parabola. That's it. There is no change in it. Because change is potential becoming actuality. In case of a ball, the ball is potentially there. So at any given point of time, the ball is only at one place. So there is no parabola in the ball's motion. Only when the potential is actualized, then the ball moves to the next place. That is what is motion. Yet, I have captured something from this motion here into this graph. What did I capture? I captured what has happened. That is, I am now going to change this x to time. So what I am saying is, it started at 0 seconds, this is 1 second, this is 2 seconds, this is 3 seconds, this is 4 seconds, so on and so forth. But now I am saying in this mathematical plot, 0 second, 1 second, 2 second, 3 second, 4 second, all are existing at the same time. Are you following me? That's how we are saying that this curve is a parabola, because we are looking at this curve as a whole and we are considering all these points on the x-axis, which we are calling as time, as existing at the same time. But in reality, that is not the case. The case is 1 second is not yet here. 1 second happens after some time, right? All the times are not there at once. And that's why in reality, when the ball is moving, there is actually change, and duration of that change is what is time. But what do we actually mean by this 1 second here? This 1 second is not time itself, it is a measure of time. There is a big difference between time and measure of time. If you recall, we defined measurement in our last lecture. Measurement is a comparison or a relationship of one object with another object. For example, let's take an analogy. If I have a table, right? I have a table. Let's say I have one small stick and one larger stick. Right? I'm going to call this as stick number 1. and I'm going to call this as stick number 2. Now, this table is a physical thing. Because it is a physical thing, it must have extension. That is, it must have one part outside another. That is, this part of the table is here, this part is next to that, and this part is here. So, one part is outside another. That's how this table exists as a physical thing. That extension is its property of length. That is, when we say, for example, when I say a rectangle has length and width, I'm not actually giving you a number that a rectangle is 2 centimeters or 4 centimeters. I'm not giving you the number. When I say a rectangle has length and width, the way you understand it is rectangle is an object or a shape that has extension, that has one part outside another, right? So there, when I use length and width, I am using it in the actual primary and proper sense of the word length, that is, having one part outside another. But I can make a measurement of this length. I can make a measurement of this length by comparing another physical thing which also has the property of length. That is, the stick 1 is also a physical thing. Because the stick 1 is also a physical thing, it also has one part outside another. So then I can compare stick 1 with table, and I can say my table, the measure of my table's length is 5 stick 1s. So my stick number 1 is the unit. So when I say my table is 5 meters, this meter is the unit, meaning you are comparing the property of length, that you have a physical thing. When you say something is 5 meters long, what does that actually mean? That means that this is a physical thing, and because it is a physical thing, it has extension, has one part outside another, and I am comparing this property of extension of this particular physical thing with another standard that is sitting somewhere in a museum in Paris called 1 meter, that with that other physical thing, and I'm saying that this physical thing is 5 meters. So this 5 meters actually has nothing to do with the property of length. It is just a measure of length. If I change now my unit to stick number 2, because stick number 2 is long, now it would just become, let's say, 3.5 sticks. This number is different, 5 and 3.5. That you should not just view it as a unit, but you should view that it is not the length that is changing, it is just your measurement, the comparison that is changing. But length in its primary sense is extension. The measure of length is comparison of the same property. The stick also has the property of length. The table also has the property of length. You are comparing one property with another property and getting a number out. So this number itself is not the property of length. I hope I'm making sense. You are comparing two things. So you can compare two things without actually understanding what the property is. And that's what we often do with time. What is time? When I say 1 second or 1 hour, what is it that you are actually doing? You are comparing one physical change. Let's say you have a clock, right? In the clock, these hands are moving. You are comparing that with another physical change. So these hands, the clock hands moving is one physical change. That is, let's say this hand goes around the clock in some X minutes or whatever. Let me not say X minutes. Let's say this goes around so many times, and then I see another physical change. Let's say sun rising and sun setting, and then I'm comparing these two physical changes and coming up with the unit 1 second. So time is duration of change, while the measure of time is comparing two changes, one change with another change. So the measure of time is a number, whereas time is not a number. Time has potency in it. That is, for example, 6:30 is not yet here. 6:30 is going to happen. It is not yet here. 6:30 will happen when a change happens. The duration of change will take us to 6:30. But when I say 15 minutes have happened, I'm just comparing one change to another change. I'm comparing whatever we are talking to whatever changes in the clock. So the measure of time is not time. You need to clearly understand that. So when the measure of time is not time, when we plot a graph like this, x versus t, and we say it's a parabola, this time is not real time. Meaning in real time, 6:30 is not yet here. It is going to happen. But here, all these time points exist at the same time, because they're just numbers, they're measure of time, they're comparing two changes. So although I have lost the essence of motion, the essence of motion is potentiality becoming actuality. That is, the ball is actually here and potentially there. So this is act and this is potentiality. The ball is not actually here. The ball is not actually at this place yet. The ball is at point A. The ball is not yet at point B. And when that change actually happens, ball comes to point B. So that potentiality is actualized. That is motion. That is change. But that kind of a potency, that kind of a change is not here. Yet I have captured what has happened into this. So this still captures some aspect of what has happened, but it doesn't have the most important aspect. The most important aspect is change. Why change is the most important aspect? Because we saw that the principle of contradiction is something cannot change itself. Right? That means for any change to happen, you need a cause. And by studying science, what are we studying? We are studying physical things to know what causes what. We are looking at effects and we are trying to figure out what is the cause. So when we say I'm looking at an effect, that is, for example, this ball going from here to there, that is the change I'm looking at. The ball went from here to there. The potentiality of ball being there has become actualized. So that's a change. And then I'm saying that this cannot happen without a cause. There must be a cause, because the ball cannot move itself from here to there. Right? Something must have happened. There must have been some cause for it. And I'm trying to understand those causes, and that's what science is. But you see here, when I convert this motion into a plot, I have captured a shape. This parabola is a shape. And as we have seen, shape comes from quantity, which is the primary property of physical things. I have captured something about this physical thing, about the ball falling, but there is no change here. There is no change here because all the time points exist at the same time. You may be tempted to think that something like dx by dt is change. This is wrong. Because when you say dx by dt, what you are actually saying is I'm measuring the slope of a tangent to this parabola, let's say. Right? When you are saying I'm measuring the slope of this tangent, this time point here and this time point here, like I said, exist at the same time. If all the time points exist at the same time, then there is no change there. Change happens when you go from, let's say, 1130 to 1131. Right? But here all the time points 1130 and 1131 exist at the same time. So in this plot, there is no change, meaning this parabola is a parabola forever. So this dx by dt is a slope. It is not really change. That is not the definition of change. Definition of change is potentiality becoming actuality. Such potentiality becoming actuality is not there in this mathematical plot. So there is no change in mathematics. This dx by dt is not a change, it's a derivative of a stationary static graph. This graph is going to be a parabola forever. So whenever you come today and take dx by dt, you come tomorrow and take dx by dt. If it is y is equal to x is equal to t square, you take the derivative today, it is 2t. You take the derivative 2 years later, it is still 2t. It is not going to change. There is no change here. Right? So when there is no change in mathematics, mathematics cannot give you causes, because cause is something that is related to change. Right? So mathematics cannot contain any causes. So mathematics really does not describe reality in that sense, because mathematics is a tool to understand the causes. But mathematics itself does not contain the causes, because there is no change in mathematics. Now, unless I understand this relationship, unless I understand that I am making an analogy, and by making that analogy, while I am capturing something about the motion of the ball in this graph, I am losing the essence of motion, which is change, by doing that. If you don't understand that, you will be confused like Roger Penrose. You may end up getting Nobel Prize, but you will make no further progress in terms of philosophy or spiritual life, because you're missing the fundamental principle. I mean, what's the point of a Nobel Prize, right? When you don't understand that electron is a physical thing. So there is no change here in this plot. So mathematics cannot describe the causes. So we cannot really describe causes, which is what science is about, in terms of mathematics. So the universe is not written in any language of mathematics. Universe is a physical universe. It is made of physical things. And because all physical things are extended, then you would, abstract out from this quantity, make number and shape, and try to capture some things about motion or other things in terms of a plot. But this plot doesn't contain changes. This leads to many confusions. Let me demonstrate one such confusion. I don't want to talk about gravity. I instead want to talk about electric field, because gravity, we will have to go into different general relativity and other stuff, which we is beyond the scope of this talk. So let's take, all of us understand charge in some sense. That charge, what do we mean by charge? Charge is a particular property of a physical thing that has mass, right? Do you know any charge without mass? There is no charge without mass. There is no massless charged particle, right? There is any charge is a property of a massive object. And then you often have written down probably Coulomb's law, or you have written down other equations like equation for an electric field. Or if I bring another charge, let's say another unit charge here, let's say this is a negative charge and this is a positive charge, then you can do an experiment and you see this feels a force, or this changes its motion and tries to go towards the negative charge, right? And you can see that there is a force, and you probably write this as F is equal to QE. Now, where is this electric field? Can anyone tell me where is this electric field? Did you understand my question? There is one charge at some distance, there is another charge at another distance. You can clearly see that the positive charge is moving towards negative charge, and you can write that in a mathematical equation, F is equal to QE, and you could say, okay, this F is equal to QE describes reality, because that's describing how charges move. So my question is, if it is describing reality, where is this E? What is this E field? Where is that E field? Is that a real thing? Is that a physical thing? If it's a physical thing, is it a substance or is it a property? If it's a property, what is it a property of? If it's a substance, how does it, look like? Are you following me? Can someone unmute and tell me if you're following me, or if what I'm saying you're not able to understand the question, or are you able to hear me, Denny? But I mean, did you understand the question? So really, a lot of people don't have an answer for this kind of questions, because we take it for granted. We get lost in mathematics, and you can manipulate equations. Yes, somebody's saying something. Okay, go ahead. Yes, you are audible now. But where is this field? Let's say it is the negative charge, but where is that field? So is this field a property or a substance? Is it a physical thing? but the charge is here, so how can its property of field be here? Because I cannot see color outside apple, right? The color is in the apple. Yeah, but whatever is far away from the charge, whatever is not within the charge, is definitely not a property of it, right? Yeah. Within the object, not external of the object. Property is within the object. Yeah, so you said so many things that are very confused, in a very confused way. So first, there is no rule. I'm not making any rule. It is what is. It is what reality is. It's not a rule. That rule itself is coming from mathematical concept. We're not following any rules here. There are no axioms that we are following. That's a very mathematical way of thinking. Reality is what it is. So in reality, you see physical things. For example, if I say this glass is hot, that hotness is in that glass. If I say this apple is red, the redness is in that apple. If I touch any other physical property, if I say this floor is hard, the hardness is in that floor. If I say this sponge is soft, that softness is in the sponge. I don't. Yes, but where is this electric field? Is it a property of the charge? Sure, but that's what I'm asking. Where is this electric field? Is it in the charge or is it somewhere else? Okay. Yeah, where is this region? What is this? What do you mean by this region? I'm trying to get you there. Where is this electric field? In the region there is electric field means what? Very good. Space between these charges. So is that space a physical thing? Very good. So this field is a property of that space, because this field is in the space. The charge is affecting a physical thing around it called the space, and this field is existing in that space. So this electric field is in that space. Electric field is a property of the space that is not captured in the mathematical equation F is equal to QE. That is only captured when you actually look back at reality and see that space is actually a physical thing, and this electric field is something that is in the space as a property of space, which is also a physical thing. So this charge here is acting on the space around it, right? And it is curving the space, right? It is perturbing the space around it because of its property called charge. The property called charge is within that massive body. That is interacting with the space around it and perturbing the space, and whatever this perturbation in the space is what is traveling out, and this perturbation in the space is what is in turn acting upon the other charge. So here there are several layers. That is, the negative charge acts on space, and this action, whatever action has happened on the space, it is propagating out, and that what is propagating out is in turn, space is in turn acting on negative charge, on positive charge. So when we say F is equal to QE, this doesn't contain the cause in it. F is equal to QE, it looks like it contains the cause, but like we saw, it's very confusing that where is this electric field? Is it a physical thing? Yes, electric field is a physical property of a physical thing called space. So it is not the negative charge and positive charge just attracting each other, because we have abstracted too much and we have completely removed a physical thing called space. We are still living in Newtonian times. That is, Newton thought that there is nothing between earth and sun, or nothing between earth and moon, right? So if you look at Newton's force, action and reaction, they would happen instantaneously, but nothing in the physical reality can happen instantaneously. The problem comes in because we are ignoring the most important physical thing in between. So F is equal to QE doesn't explain the motion of the positive charge towards the negative charge. What explains it? The cause is the negative charge perturbs the space around it because it has a particular property that can change the curvature of the space, that is the charge. And because there are these perturbations in space around it, these perturbations in space propagate, just like how if you cast a stone in a water pool, the water wave would propagate. In the same way, it would propagate, except this space is not massive like water medium. The space is non-massive. It doesn't have any mass. That's what Einstein showed, right? Space is non-massive. But it doesn't mean it's not a physical thing. Space is still a physical thing. It can have properties like electric field. So this charge is influencing the space, and this space, in this space, this is a physical thing, and electric field is a property of that physical thing, and that's what propagates out to the positive charge. This simple realization that space is actually a physical thing, that, you know, when looked at masses, that's how Einstein saw that Newton made a big mistake with F is equal to g m1 m2 by r square. That Newton excessively abstracted, using mathematics, excessively abstracted the most important thing in between. Einstein didn't have a supercomputer. All that Einstein did was, he was not blown away by the math of it. He looked at the actual physical reality and identified that there is actually this space, the physical thing that is in between. Because he asked himself the question, what is this electric field? Is it a physical thing? Yes, this must be a physical thing because it's moving other physical things. It cannot be something non-physical. If it is a physical thing, is it a substance or a property? Clearly it's not a substance because it cannot exist by itself. It is existing as a part of something else. And so it must be a property, but it's not a property of the charge because, you know, this electric field is there around the charge, not within the charge like other properties. So then what is it a property of? Then there must be something between these two charges, and that something is a physical thing. And that's how he realized that there is this space, and that's what gets curved because it is a physical thing. When you say space bends and warps and all this, you mean that it is actually a physical thing. So you can see here clearly how much of physics is actually lost in the equation F is equal to QE. I hope I made sense there, that the electric field is a property of this physical thing called space. So whenever we are using mathematics, we must understand that mathematics itself does not contain change. Therefore, mathematics itself does not contain causes, and we must always go back to physical reality and not think about it in a very confused way. Like, for example, saying positive charge attracts negative charge, that's what reality is, that's how it is. It doesn't explain anything, right? It doesn't explain why positive charge is attracting the negative charge. It doesn't explain that there is actually something called, you know, the space, which is a physical thing, right? And then that's how it is getting communicated, and that's the physical thing that's actually happening. It doesn't explain that. And if we go deeper and actually ask ourselves the question, I think we are a little bit off 6:30, so I'm going to end it with this question, which we can take up again later. And now, just like charge or mass or charge or spin or whatever properties you can think of, what is actually mass? What do we actually mean by mass? We say mass is a property of this physical object, but what is mass? Let's say, okay, mass comes from, let's say I have gold. This is what, again, Uddalaka asked Shvetaketu, right, in Chandogya Upanishad, that let's say I have a piece of gold. It has some mass, you say. Where does this mass come from? You can say it comes from gold atoms. okay, where does the mass of gold atoms come from? Then you can say it comes from protons, neutrons, electrons, little bit, whatever is in there. Then you can say, okay, fine, protons. Where does the mass of protons come from? Then you can say, okay, it comes from quarks and the energy that binds them. And then you can say, where does the mass of quarks come from? And then you go back to saying, oh, it comes from energy. But what is this energy? Is it a property or is it a physical thing? You use this equation called E is equal to mc squared, but what is this energy E? Because this m is a physical thing. I can touch, feel and see this m. It's definitely a physical thing. But what is this energy? When I say, an electron is going at speed of light, E is equal to mc squared. There's an atom bomb or a nuclear bomb, some mass changes and then you get that as energy out in a nuclear reaction. What is this energy? Is it a physical thing? Is it a physical property? Because when energy is there, what is it a property of? Just like the electric field. This energy is a property of, again, the physical thing called space, right? So you have to think about even more deeply, what does mass mean? Or what is even energy? Because it's very easy to write down an equation, but like Roger Penrose was saying, it comes down to equation as the definition, but equation cannot be the starting point. A physical thing is starting point. Only when you explain physical things in terms of physical things, then you have true causes and effects, not when you explain it in terms of mathematics. So we accept these symbols as M or Q or S for these degrees of freedom, we call them, and we are stuck in our mathematical box. And there is a theorem that was proven by Gödel, it is called Gödel's Completeness theorem, where he shows that if you are stuck in a box like that, you can never explain physical reality. Because there must be always, validation from physical reality. So just by calling mass M as a symbol, you don't understand mass. Just by saying E is equal to mc squared and saying mass and energy are equivalent, they're not equivalent. Because M, mass, is mass of electron. E, energy, is energy of space. Right? So we have to make those distinctions, and I would like to stop here, and so that you can officially end the thing, and then we can carry on with the questions. Okay. Right. Yeah. So we have to understand what is infinity first. What do you mean by infinity? No, we don't confine. Yeah. Space. Yeah, space is a physical thing because it can bend, it can warp, it can it can react to whatever is there, mass, charge, right? And you can measure that, how it warps and how it changes, right? And so that's why it's a physical thing, right? If space around the sun is not physically changing, if it's not a physical thing, right? What is it that is changing around the sun that would make a light ray bend, right? So we can measure that, because that gravitation of sun or the electric field of this charge is in space. Why not? I'm able to stretch my hand. How am I able to stretch my hand? Let's say if there is nothing here, would I be able to stretch my hand? That nothingness is a mental construct. It is nothingness. I can say there is something, or there is no thing that is nothingness, like we have seen in the last lecture, that nothingness itself is non-existent. I'm able to stretch my hand because there is something here, right? That's why how I'm able to stretch my hand. And what is that something here? It cannot be nothingness. It is something, right? Because clearly that exists right there. So that's how I'm able to go there. I'm able to stretch my hand. So that means the space itself exists, right? That's a physical thing, and that's what you are made of too, right? Sanam. Yes. So you so that's why it's not very very important to make a distinction. So this confusion is coming. We have to address the root cause of this confusion. Root cause of this confusion is coming because in your mind you have abstracted charge and you have abstracted mass as two different things because you use m and q. But where is this q? Where is this charge? It is a property of a physical object. That mass is also property of the same physical object. If I take an electron, right, that electron has mass, that electron is the same thing that has the charge. It is not that the electron's charge gets activated when you put an electric field, or it's not that the mass gets activated when you put a gravitational field. All these things are a property of that object, right? So when you say the charge doesn't respond to gravitational field, you are sort of abstracting charge out and just looking at charge itself as some physical object. When we say charge in electrostatics or electrodynamics, what we mean is a massive body that has charge. But instead of saying a massive body that has charge every time, we just say charge, right? And so this charge is not an abstract property that exists outside. It exists as a property of a massive substance, where mass is also a property. So all these things get affected simultaneously. Like it's not that gravity acts first and electric field acts next. It's whatever it is. All these things, the physical thing has certain properties. That's why, we are able to write F is equal to QE because there is electric field and this object has mass. Because it has mass, it can gain this momentum, it can gain this impetus, and that change of impetus is what is force. Change of momentum is force. And that force, when I am writing F is equal to QE, what I'm saying is MA is equal to QE. That this mass is what is moving, right? You can say the positive charge is going by F is equal to QE, but there that F is the force on the charge, that is MA or dP by dt. That is still mass. So this electric field is still moving the mass because charge exists only as a property of this massive body. Does that make sense? And yes. Yes. No, it is not. You're thinking again about elementary particles. I'm not talking about elementary particles. I'm talking about, let's say, you find whatever is the smallest thing. Let's say, hypothetically, you have something that's the smallest thing. And whatever it is, for example, electron. We know we have done enough experiments now to know that electron has no internal particles any further, right? It is not that in future some more experiments can be done where it can be seen that electron would have internal parts. It's not that. Why so? We'll have to go into more details, but we have seen we have basically seen the electron change substantially, meaning the electron can, if you go at relativistic speed, this entire electron can basically become, disappear and become energy of space. So we can see that E is equal to mc squared there with an electron, for example. So we know that an electron doesn't actually have any parts. I shouldn't say any parts, I should say any more elementary particles, right? So, but electron has extension, it has a size. So anything, let's say whatever, it's not, let's say if you're not convinced with electron, let's say something else, whatever it is, how does it get mass? Because we have space, we understand space, that is space is extended, it is there, but the space itself doesn't have mass. From this space, how did mass actually come about? when the Big Bang happened or whenever the creation happened, how did mass actually come about from the creation? Because there is God. God is non-physical. God doesn't have any mass. God is not a massive body that is sitting there. God is non-physical. But somehow this universe came out of that. Somehow this physicality came out of that. And in this physicality, we do see that there is this mass. So how does this mass come out of something that is non-physical? That's the question that I'm asking. How does this property of charge come out from God? When we say God, it came out from God, or there must be some uncaused cause for the beginning of this universe. Because this universe cannot come from nothing. It must come from something. Because nothingness is non-existent. And that something cannot be physical. Because if it is physical, that also must be caused by something else. So whatever is the beginning, that is the uncaused cause, and that is not physical. So how did this physicality called mass or extension or whatever came out from this non-physicality or God? How did that come? For that, we use mass as just a symbol. M is equal to 10 kilograms. It's a measure of mass that we often deal with. We don't ask actually what is mass or what is inertia. Does that need a cause? Right? So it's not about identifying the smallest elementary particle, but it's rather about identifying a deeper mystery that how did physicality originate from the original non-physicality, original uncaused cause? I hope that, yeah. Okay. Okay. So we have to, whenever we talk about photons, we have to first ask what is a photon, right? What's a photon? What do we mean by a photon? Is photon a massive particle, a massless particle? Is it a virtual particle? Is it a real particle? Because there are different types of photons. There is virtual photons, there are other photons. But if you're talking about light, you have to also understand what is light. Like we have seen, electric and magnetic fields are property of space. So light is a property of space. It is what exists in space. So light is going from one point to another point in space, and if you want to look at it in terms of photons, that's called first quantization. This goes the other way. It is unlike the quantization of electrons, which is called the second quantization. That is, electrons behave, things behave like particles. Like if I throw a ball behaves like particles. So things that it is made up of, like electrons or protons, you expect them also to behave like particles. But we see that if you have 1 million electrons that are going from lanthanum hexaboride filament into 2 slits, if you do that experiment, one electron after another, then after 1 million electrons, you see a wave-like pattern. So it is not that the electron is the wave. It is that if you look at 1 million electrons, while you cannot predict the exact motion of an electron, like how you can predict the motion of a tennis ball with Newton's laws, nonetheless, you can say something about the electron motion by observing 1 million of those electrons. So when you say light, interference pattern forms on a screen in an electron double slit experiment, this interference pattern does not correspond to a single electron. It corresponds to millions of electrons. So we're looking at that wave nature in these millions of electrons. And that's what we see as a wave. That is going from particle to a wave. So there you have a real thing that is physically extended, and you are using a substitute, statistics as a substitute, probability as a substitute, because that's the best thing we can do. From whatever experiments and measurements we have, that's the best way we can describe it. And that's how we're doing second quantization, treating something that's extended, that's a physical thing, as a wave, not in terms of a single electron being a wave, but I can describe the motion of a single electron in terms of an ensemble of million electrons. In case of photon, it's the other way around. It is, you have light that behaves like a wave. That is, light is made up of electric and magnetic fields. These electric and magnetic fields are properties of space, and perturbations in these electric and magnetic fields in space or any field in space. For example, gravitational field is also a field in space. So it is just like electric and magnetic field. So even gravitational wave would travel out at the speed of light, right? So its light is basically a property of space that comes from its ability to be affected by other physical things like charge or mass or massive objects. There we don't have like the electron's beginning point. We're going the other way around. That's why it's called the first quantization. You're going the other way around. So really there is no understanding of photon as a physical thing. Often, especially in quantum electrodynamics, a photon is made up as a mathematical tool, like a virtual photon. It's made as a mathematical tool to make things easier. It's not a real physical thing. But there is some reality to that photon being a particle, in the sense that even space is an extended physical thing. So space must have one part outside another. So there must be one smallest part of the space, right? Which people think is Planck length. But I don't know about that. But there must be one smallest part of the space, and photon size must have to do something with the smallest size of this. In the sense, it's often described mathematically in terms of, if you have Planck length and speed of light is the maximum, then you can calculate a delta t, the smallest change that can happen, and the extension of photon, the real photon, must have something to do with that. I know it's a very long-winded answer, but I hope I answered Kishore sir's question in some way. Is sir still here? Okay. Did I answer your question, sir? No, I'm not saying photon is extended, sir. I'm saying that virtual photons are just mathematical tools. They're not they're not they're not physical things. So it is physical things that have extension, right? So we cannot say that the virtual photon is any physical thing. But space, yeah, the real photons. Okay, go ahead. Yeah, the real photon we don't actually. Yeah, the real photon. The real photon is. I'm not sure we actually understand what a real photon actually means, because it's often sort of completely used as a mathematical entity without any physical meaning to it. But the way I see physical meaning to a photon is space is a physical thing, and the base property of any physical thing is having extension, that is having one part next to another, that we can see in space, that space has one part next to another. That's how I'm able to stretch my hand or move from here to there. And what is energy? What is energy? Is it no, I will stop you right there, because packet of energy, where is energy? What is energy? Is energy a substance or is energy a property? So if energy is a property, here in this case you are saying packet of energy. So this energy is a property of what? What is the physical thing that it is a property of? Very good. It is a property of the space. That's right. Right? So the space itself is a physical thing, and energy is a property of that. So photon is a property of a physical thing called space. So when you say that photon is a property of a physical thing called space, physical thing, space is physical thing, so space is extended. So as a property of that, you can say photon, you can think about photon as extension, because any space is a physical thing, and so it must have extension, so it can exist only in that extension. So in that sense, photon as a property of space is extended because space is extended. But there is no such thing as energy by itself. Like energy cannot exist by itself. It exists only as a property of something. And that something is a physical thing like space. So that space is extended. So this photon, which is you're calling a packet of energy, exists as a property of a space, and that space is extended. that's what it is. Photon, yeah, the electromagnetic fields are a property of the space, right? So yeah, so that's right. Yeah, they can be treated that way, right? Yeah. So okay, go ahead. So we have to understand the difference between action and reception, sir. So any physical thing, in last lecture I have talked about these properties. There are extrinsic properties of physical things. Two of the extrinsic properties are action and reception. That a physical thing can act on another physical thing, and a physical thing can receive from another physical thing. So now if you have two charges, one charge is positive and one charge is negative. So the positive charge is a physical thing that is acting on another physical thing, which is the space. Now this physical thing, space, has received the action from the charge. Because this physical thing called space received the action from this thing, this action in one part of the space is acting on other part of the space, right? And then same thing happens until it reaches the negative charge. Now the space around the negative charge is also, that's also a physical thing. So it can also act on another physical thing called this negative charge. So now this negative charge is receiving the action from the space that's immediately surrounding it. And no, here there is no, that's that is you're going one level above, sir. But the problem with that picture is you're going to the interaction of fields. But even let's say you have taken, that's why we always take a unit charge, and let's say you take 1 coulomb of negative charge and say a million coulombs of the negative charge, right? So the field of the negative charge is so overwhelmingly high that you can just basically, for now, in your, like, just like how we turn off friction for studying mechanics, like that you can in your mind turn off the field of the positive charge itself. It's sort of a unit charge that's much smaller, let's say, right? So then, yeah, so that then basically we have to include this action and reception. So actually in Coulomb's law, if you write the force, you write it as k q1 q2 by r square, right? Why is there a k? Yeah, what is that permittivity? Why should there be k? No, but where does it come from? Why should it be a particular value? Or even for gravity, why should there be a capital G and why should it be a particular number? No, it is because action and reception are different. So charge has two different types of charge. One is charge that acts. So the charge that acts on the space is not the same as the passive charge that receives from space. So they're different. It's not cause and effect. It's action and reception. They're two different things. It's not action and reaction. It is action and reception. So I can act on the space and space can act on me. That is two different things. This is not cause and effect. It's not an action and reaction, right? So no, you cannot. Cause and effect is different, sir. Right? Cause and effect is the space can act on me not because I can act on space. Space can act on me independent of me. For example, like there is some object, right? So the electric field from somewhere else can act on this object irrespective of whether this object is acting on the space or not. You're thinking about as action and reaction, like earth is pulling moon, then so moon is pulling earth back. It is not that kind of a action and reaction. This is action and reception. That is the ability of the object to act on space or ability of the object to receive anything from space. It is not just from the electric field, but from anything else as well, right? So but that is not the right explanation though, right, sir? Because that's not cause and effect. I mean, it is not up to the interpretation, right? That there is a reality, and that's the thing, that we are describing reality as what is out there. So that what is right or what is wrong or what is correct is determined by that reality and not by the interpretation, right? So that's what we have to bear in mind. Okay, that's we can take that up maybe in the next lecture or something like that. So I think Sudhanshu has a question that he typed here, and so he says, as a physical thing with a rational thinking ability, what according to you should be the attitude of a physics student in understanding our creation? And if mathematics is not the language for us to understand it, which language should be used? How effective will that language be in terms of communication? So very good question. So first of all, you are not a physical thing. You have physical body, right? And you have mind, but your intellect is non-physical. Because like I mentioned, when I say square, you are not thinking about one particular square. You can think about any square. You understand square in general. And the ability to understand generalities, not particulars, is intellectual, and that is non-physical. So you are not a physical thing, you have a non-physical intellect, right? So you said rational thinking ability. I see that that's what you meant probably by intellect. But you know, a human being is not a physical thing. A human being is what we call as a form matter composite. That is, you have both physical body and you have mind and you have intellect. Don't mistake intellect with your mind. There are three layers. There is sharira, there is manas, and there is buddhi, right? There is body, mind, and intellect. So this intellect is what can understand generalities, and the mind is the thing that is sort of organizing this orchestra of senses and sort of letting the intellect derive from the senses. So mind is sort of the interface there. And so mathematics, it is not that mathematics is bad. Mathematics is very, very important for us, because only by using these symbols and manipulating these symbols, we're able to capture at least something from the physical reality. But what we must not forget is the equation corresponds to a line. There is no line in the equation. It is merely representing the line. And when I say a parabola, the parabola is not motion. And there is no motion in parabola and no parabola in motion. So we must always connect it back to reality and understand the causes from reality. Mathematics is good for, it's like a tool, it's like a screwdriver. A screwdriver is good for doing something like unscrewing something, but you are building something else that depends upon whatever you want to build. So use this as a tool, use mathematics as a tool, but don't forget what it actually is and what it actually means. Like how Roger Penrose was saying, electron is something that obeys Dirac equation. That would be a very poor way to understand reality. So the way to understand reality is you have come up with a mathematical equation, understand what is the essence of that equation, like F is equal to QE. What does it mean actually? This electric field, the charge is acting on space, and space is acting, it's propagating from one part to another part, because space is a physical thing, and this is acting on another charge. That is physical understanding. So don't start and begin and end with mathematics. Start with reality, mathematize it, use mathematics to get forward, and then come back to reality. It is like use a car. You have a car, right? You use a car to go from, let's say, Bangalore to Hyderabad, right? But once you get to Hyderabad, then get down and walk in the streets, right? That's how you can see Hyderabad. Don't be in the car, right? If you are in the car, you are not really, seeing it. You have to get down and go around. In the same way, use this mathematics as a tool, like a car, to go fast and to go farther. But at the end of the day, you have to come down and connect it back to reality. You have to understand what actually Dirac equation is and express Dirac equation in physical terms in normal language without using any jargon. And then that's how you can understand what the universe is. And whenever you have questions like infinity, try to, the main important thing that a physics student must have in his or her attitude is that you must question yourself, what do you mean by these terms? Like I think you mentioned infinity. What do you mean by infinity? Infinity doesn't exist in reality, right? Because infinity is a mental construct that you look at finite things and derive this concept of infinity, that this is here and that is there. So I can mentally think of something that's very, very far away, that is ultimately unreachable, right? But there is no such thing called infinity in reality, completed infinity, because completed infinity is against the principle of non-contradiction. Because if I have infinity and infinity plus 5, both are infinity, then how can infinity be both infinity and infinity plus 5 at the same time? It cannot be. That is against our physical experience. So when you put your physical experience back, you understand that infinity is a being of reason or a mental construct. So you become more careful about using these as just numbers, right? And so that the attitude should be to question yourself on what each word actually means. And to understand our creation, we must separate what is a being of reason and what is a real being. And that can only be done by actually looking at the difference between mathematics and physics. Like nothingness is a being of reason. That is, I know something, that's how I know spoon, that's how I know there is no spoon, right? Without spoon, there is no meaning to there is no spoon. So nothingness is a being of reason, or it is non-existent. So you cannot use that as the beginning point of the creation or the universe. There must be something, right? And that something cannot be physical, because if it is physical, it must also have another cause. So to think about it from that philosophical point of view, by defining everything very clearly, is what should be the attitude. And I hope I answered all your 3 points. Okay. I feel there is another one from Sahil. I feel the truth is we do not and cannot understand things fully. Okay, let me stop right there. What is truth, Sahil? Yeah, what is truth? Okay, reality. So truth is confirmation of our mind to reality, confirmation of our mind and actions. But a better definition is satya. Satya means that which exists. Satya means that which exists, right? So that which exists. What do you mean by you cannot understand fully? Because you are that which exists, right? You are that which exists, so you can understand it fully, because you are that aham brahmasmi, and you have to just work deeper and go into meditate and contemplate and understand the universe. Because if you don't understand the universe, there is really nothing else, because the human nature itself, we are here for truth, we are made for truth. Our ultimate goal is to become satyam itself, right? So if we cannot understand it, there is no point to human life. And if there is no point to human life, there is no point to the universe. If there is no point to the universe, then it all becomes meaningless, right? And when you say it is meaningless, it basically says that, it comes back to say that this thing doesn't have any essence, because not having meaning is not having essence. But it is something which exists. Anything that exists must have an essence. And so you are sort of contradicting yourself when you say the truth is, I feel the truth is we do not and cannot understand things fully. Let's say we do not and cannot understand things fully. Then if we cannot and do not understand things fully, then that is the truth. Then you have understood the truth, right? You are understanding that you cannot understand. Then you have understood it. It is like saying I do not know. But when you say I do not know, who is it that does not know? Then if you say I do not know who I am, then again you are going back in a circle, you are contradicting yourself. So that first sentence itself, there is a problem with that, right? And all we know is how to quantify and formulate. I mean, how much ever you try to break things down, eventually you will get stuck somewhere. No, you will not get stuck somewhere. You will get stuck somewhere if you are going like Roger Penrose, thinking that mathematics is everything, that you don't identify what is actually mathematics, where it comes from, and you actually don't think about it in the right sense from physical perspective of things, that's when you will get stuck. Because like even in simple formulation like F is equal to QE, you will get stuck at what is electric field, because you have completely abstracted things out and you have forgotten reality, you have cut off this reality, and you are just manipulating equations, right? It is like saying I have learned the recipe for paneer tikka masala. If you give me paneer, tomatoes, onions, and sometime I can cook paneer tikka masala, but I don't think I can ever grow paneer. That I don't think paneer can ever be made. No, paneer can be made. That's how you are making paneer tikka masala. You have to understand that there is much more than the recipe. There is actually a way to make milk, way to get a cow, get milk, make paneer out of it. There is a process there. You can understand that. Just you should not be stuck in this box. You should actually look at the reality where paneer is coming from. Then you can know that paneer exists and paneer can be made. And this getting stuck in this recipe of mathematical manipulations is what makes you get stuck. Like Roger Penrose said, when it goes to electron, he said, yeah, electron is something that obeys Dirac equation, because that's where you get stuck. You cannot explain anything further, because you have built up all this poetry of mathematical symbols and you have forgotten what they actually mean. So you can solve problems and you can guess that the G factor of muon should be this much, but you cannot explain what magnetism is because you're stuck in symbols. But if you're not stuck in symbols and you're rooted in reality, you can understand all the reality. In fact, that is the goal that we have as humans, that when you say that there is a spark of divinity in all of us, that spark of divinity is our intellect, and that intellect is trying to conform with reality. That intellect is trying to become, it's on a journey to become the truth itself, and that's the whole goal. So we can understand things fully. It's just that we have to think deeper and better without limiting ourselves and without just being lost in mechanical manipulation of symbols or words. If we think deeper, we can understand everything. And in fact, that's human nature. Human intellect is made to understand things. I hope that answered your question. Sorry? Yeah, a difficult process doesn't make it impossible, right? And it is difficult because we have made it difficult. It is not really difficult, right? As Vivekananda puts it, it is the easiest thing to do, but it is us who have made it difficult. Anything else? Any other questions? Okay. Thank you all. If there are no questions, I think I'll take your leave, and we'll see if we want to do what we want to do in the future. Saram. Saram, everyone. Yeah. Okay.